Okay, so you should have practiced your balancing chemical or balancing nuclear equations, and we're going to talk about half-life and then finish the rest of this chapter. So a half-life is going to be the time in seconds, minutes, hours, days, years. The units can differ, but it's going to be the time required for half of the sample to decay. So if we're starting at 100%, it's what it takes to get to 50%. If we're at 50%, it's what it takes to get to 25. And you just do half and half and half all the way down until you get to zero, which in theory you will never get to zero. If you know anything about exponential decay, you know that you can get close to zero, but you're not actually going to get to zero. Each isotope is going to have a characteristic half-life. So we can see that here, tritium half-life is 12.26 years. Carbon-14 is 5,730 years. So this is used for carbon dating, bones, paper, anything that has carbon in it. At one point, life associated with it, you can do carbon dating. You have iodine, which is used in imaging for thyroid issues. Half-life is 8 days. Xenon, which is used for bone scans, 5.27 days. Uranium, 4.51 times 10 to the ninth, which is billions of years. And then potassium, which is used for dating rocks, is going to be 1.3 billion years. So a long, long time. Now the way this looks is, we're starting off at 1,000. We start the timer at 1,000. The first half-life is going to be however much it takes to get from 1,000 to 500, because that's half. Then you're going to go from 500 to 250, 250 to 125, and then it's going to be, 62, 30-ish, 15. You can see it goes down. And then this is what the half-life curve will look like, which is called exponential decay. And the half-life curves will follow this. No matter what the actual half-life is, seconds, minutes, years, hours, it's always going to follow this exponential decay curve. The only thing that's going to differ is the amount of time, the units. Now, radiation units, we measure radiation in two ways. One is the amount of radiation that's being released by an object, like a nuclear power plant, a rock, your body. The second one is radiation that's absorbed. So we can either measure with like a counter. It's called a scintillation counter. They'll point it at it. If you watch the video of Chernobyl a while back, he had that little thing that was beeping, which tells him how much radioactivity is in the air. But there's also going to be badges that people wear that tells you how much radiation your body is potentially absorbing. And ideally it should be none if you're wearing a counter like that. But those are the two ways, what's being released and then what's being absorbed, because they're not always the same thing. Now, no matter what, we are always exposed to some sort of natural background radiation, which we're going to talk about. The upper limit for that is around 0.5, and this is because of jobs, medical scans, things like that might cause you to have more radiation than the average person. You don't start to see observable effects until you get to be about 25 rem, which is much higher than the upper limit of annual exposure to the general public. And at that point, you'll start to see reduced blood cell counts. So we start to see some effects underneath the tissue. At 100, you'll have fatigue, other symptoms because of radiation sickness. Once it gets up there, you'll start getting the bone marrow damage, possibility of leukemia. Then there's a lethal dose for 50% and then a lethal dose for all. Now down here, these are the main concerns with nuclear meltdown or nuclear release, is that you'll be exposed to such a high limit that you're going to get acute sickness or chronic sickness. So acute is something that happens right away. It's not, it's acute. The response from the body is immediate. Chronic is a long-term issue that we tend not to see because it is much later in life, or because the amount you're getting exposed to is such a lower level that it's not causing acute issues, but it will cause long-term chronic issues. So background radiation is from natural sources. So there's nothing we can do to get rid of that because we live on Earth and we revolve around a sun. But individual life experiences also increase the yearly dose. So cosmic rays from outer space, can't do anything about that because we live on Earth. Earth's residual radioactivity, also can't do anything about that. That's all part of that background we talked about. Food is radioactive, the ground is radioactive, trees are radioactive, everything has some sort of natural radioactivity. Now, the other causes that might expose you to more are getting medical x-rays. If you fly in an airplane, higher up in the atmosphere, you get a higher level of radiation each year. Old TVs used to have radioactivity associated with them. The big box TVs that you just don't see anymore. Not the box TVs that are, maybe 10, 15 years old, but the box TVs which are like 20, 30, 40 years old. So TVs you've maybe never seen in your life. So this isn't so much of an issue anymore. Another source would be basements. Basements are a place where radon tends to settle because radon is a very heavy gas and it's radioactive, and so it settles down in basements. And if you have a basement in your home, then you might have a higher level of radiation each year. Now, the consequences of radiation exposure are of course, DNA disruption. These are aside from your these chronic issues we talked about down here, but DNA disruption long term, free radical production long term. But there's currently no agreement about the impact of long-term low-level exposure. There are people who think the long-term low-level exposure contributes to cancers, but there's really no evidence suggesting that that's a strong link. And so it's still uncertain if it's because it's long-term low-level or if there's a short period of high exposure, if there's any difference between long-term low-level and short-term high-level exposure. So currently no agreement, but of course it's best to be judicious when you're making decisions about exposing your body to radiation. So nuclear fission is the type of reaction that we're talking about, and it's where something that's heavier is going to split into something lighter. So we have uranium. Uranium splits into krypton, neutrons, barium. You can see that it's kind of like a cascade, a domino effect, if you will. So we call this domino effect a chain reaction. And this is where once we start the reaction with uranium, we hit it with a neutron, you can't stop the reaction. It's going to then domino, and it's going to continue to react until the fuel is spent up. So one possible reaction leads to many others. One neutron in, and then you get two or more out, and you can see that the krypton will go on, the barium will go on, and then down here we have quite a few products being produced. Now, there is a key component required for this chain reaction to occur, which is called critical mass. You must have a sufficient amount in concentration to produce a chain reaction. And so most of our nuclear power plants are not going to house such a large amount that it's dangerous. They're going to have a small amount so that if there is a nuclear meltdown, it is a very small amount. Not to say that it doesn't make it unsafe, but the critical mass is key. It's like the initial flick on the domino. The critical mass is what causes the domino to fall, just like the finger pushes the domino over. So nuclear power plants are very complicated. You're going to see a video, or there'll be a link to a video. I encourage you to watch it, which describes the different parts of it. The key parts are the reactor core. So this is where the nuclear material is kept. And you have this loop that goes through. And it's going to be very hot, so heat associated with it, which is going to generate steam. The steam is going to be transferred over to a turbine. So remember, turbines are like the big wind turbines out in the fields. The turbine is going to begin to spin. As it spins around, that's going to generate electricity, goes to a transformer. You have cooling towers, auxiliary buildings. They're very, very complicated. You have them housed in a containment building, safety sprinklers, control rods, and so make sure you watch the video to kind of get an idea of how all of these things work together. So what are some problems? Well, problems with nuclear power plants is that there is, once the fuel is used up, there are spent fuel rods. So the things that fuel the reaction, once they're used up, they still contain what's called fissionable materials. So uranium-235, plutonium-239. And so because it still is fissionable, it still is radioactive, and it's a matter of national security. You don't want to just go dump it somewhere because people will steal radioactive material to make bombs and other things like that. So we have to be very judicious about how we are disposing of the material. So right now, most of these spent rods are being housed in a cooling reservoir, because there's also not agreement about taking the material and just reacting it all the way to make it something that's safe. Because there's a belief that because the material is still fissionable, that it's useful in other ways, and it is useful in other ways. There's just not agreement about what's best. Is it best to use up all the radioactivity and then dispose of it as non-radioactive material? Or is it best to recycle this fissionable material for another purpose? And that would help avoid the national security issue, but it would mean that we're not wasting the potential energy, because we could still harness a lot of energy from uranium-235 and plutonium-239. So, long story short, in the U.S., disposal issues are not settled. In other countries, they have a recycle program put into place so that they're making use of the material. But right now, we haven't gotten there yet. Long-term plan is they will most likely be stored somewhere safe until decisions can be made. We have probably, according to your book, about 1 football field in area 4 meters deep of spent fuel rods that we have yet to do something with. So it's not a ton, but it's a good amount. The other problem with nuclear fission plants, like we've been talking about, is nuclear meltdown. So we have 3 Mile Island in 1979, Chernobyl in 1986, and Fukushima 1 in 2011. All of the meltdowns were for various reasons. Your book has about a two-page reading over the 3 nuclear meltdowns. Make sure you go and you read about the nuclear meltdowns, what caused them, what was learned from them. We learned a lot from 3 Mile Island, a lot from Chernobyl. Fukushima happened because of a tsunami, so it was not a man-made issue as much as 3 Mile Island and Chernobyl were. Fukushima was kind of a natural disaster that unfortunately started the chain reaction of the nuclear meltdown. Nuclear fusion, on the other hand, is the opposite. It's less massive nuclei coming together to form something more heavy. Now, the wonderful thing about nuclear fusion is we have a great example for us to study the possibilities, and that's because our sun and all the other stars are powered by nuclear fusion. The requirements for fusion are high temperature, high density, and then a sufficient containment time. And containment is just like being confined. You have to have enough of the material in such a small location, being with such an intense pressure at such a high temperature to ignite the sun. So when God said, "Let there be light," that's essentially the sun turning on, but it did so with a large amount of confinement and a high temperature and a lot of hydrogen around. Each time a star is born, these conditions are being met. So what's happening is you have this proton-proton chain reaction. 2 hydrogens come together, then 2 deuteriums come together, then 2 helium molecules come together to form helium and hydrogen. So they're taking lighter molecules, which are actually much safer for us than the heavier uranium nuclear meltdowns, and creating a lot of energy. So there is currently a lot of research being done on trying to replicate nuclear fusion on Earth and to create power plants that will run on nuclear fusion type energy instead of nuclear fission, which removes that concern about nuclear meltdown and national security and all of the other things that we have on the previous slide we talked about. So the problems associated with fusion, with recreating it, is that while nuclear fusion would be a better source of energy than nuclear fission, there are 3 important factors we can't recreate. And there's 4 here, but I'm going to tell you which are the 3 that we can't recreate. The first is the temperature. The requirement of the temperature is 100 million degrees Celsius. So what this means is we have to have materials that can withstand that temperature, and we're limited because the materials we have wear out quite quickly at that heat, or they don't withstand the heat, or they start to react with the heat. The second is the density. which is the concentration of the hydrogen nuclei must be very high. So we have to have a lot of it in a very small area. The third variable that's here is the hydrogen nuclei must be confined for just a few seconds. So that doesn't sound hard. Like it's only a few seconds. Surely we can hold it together. But the amount of pressure that's required to make that happen is immense. Your book quotes it to be about 10 atmospheres, which is 10 times the pressure of our atmosphere, which is about 1. And that's a lot of pressure. It's not something that, again, we have a lot of materials that can withstand that type of pressure. So the parts we struggle with: temperature, pressure, and time. While density is going to probably be an issue until we can overcome the temperature, the pressure, and the time requirements, we really won't know if the density is going to be sufficient enough. So there is still a lot of hope that this will be a source we can use in the future to harness energy, but for now there's a lot of problems that we haven't yet quite figured out. I think there's probably a 20-year goal by 2035, I think, to get nuclear fusion going in a country as kind of a test pilot, but there's a lot of hurdles for them to overcome. So this ends your chapter 12, or chapter 11. Make sure that you watch the video about the nuclear power plants and that you submit your notes when you are done.